All right, it is 1:02, so I'm going to go ahead and get started. Thank you everyone for joining us today. My name is Savannah Tracy. I'm the Communications Manager at the Cleveland Water Alliance, and we're really excited today to be partnering with Dr. Joe Ortiz of Kent State to present this webinar. Before we kick off, I'm just going to take a brief moment to talk about Cleveland Water Alliance for those of you who don't have as much background on us. I also, throughout the presentation, I want to encourage you all to submit questions. We'll be allowing about 10 minutes at the end of the presentation to answer all your questions, but you can enter them throughout the presentation in the Q&A box that you'll find on your screen. So just a little bit about us. The Cleveland Water Alliance is a nonprofit organization that collaborates with a cross-sector of partners to really accelerate implementation and commercialization of new innovative technologies in the water space. We're what's called a water innovation cluster. We're based here in Northeast Ohio, but we work Lake Erie region-wide. Our mission is to foster a robust Northeast Ohio water innovation and technology ecosystem of economic development and commercialization through partnerships with industry, with academia, and government institutions. At the core of this mission is that we recognize that water is one of Northeast Ohio's most valuable and often undervalued assets. We all know that the Great Lakes contain around 20% of the world's surface water, fresh water, and provide for 1.5 million jobs in the Great Lakes region. And for us, centering the value of this water and the vast opportunities it brings looks like a couple of different program areas. So the first one that we focus on is innovation. These programs are about the development and implementation of new technologies, whether that's research, academic, or in the private sector context. The next piece of this is the connection between innovators on a broader innovation ecosystem. Cleveland Water Alliance serves as a hub for the Lake Erie region to connect research institutions with private companies, with utilities, with incubation services to really try to de-risk the process of innovation and accelerate the time it takes technology to move from the R&D stage to real technologies with impact. And finally, it's something that we call Elevate, which is, I apologize. It gives us the capacity nationally and internationally to talk about Lake Erie and the Great Lakes as a hub for this kind of innovation. We bring partners and collaborators into new spaces and try to offer them opportunities by using Cleveland Water Alliance as a platform to elevate the narrative around water innovation and the blue economy. And this next slide is just to quickly give you a sense of the kind of partners that we have engaged. For us, industry is a huge core of that collaboration. A lot of our members are engaged in innovation from a corporate perspective, and we work with companies like Xylem, Connecticut, Odie, YSI, and more. We also work closely with utilities like the Northeast Ohio Sewer District and Cleveland Water, academic institutions like Kent, of course, government agencies, nonprofits, and foundations across the region. And all of these supporters we work with to come together with a commitment to engaging in the innovation ecosystem. And one more time, I just want to encourage you to submit questions as they arise throughout the presentation. And with that, it is my pleasure to introduce Dr. Joseph Ortiz today. Dr. Ortiz is a professor of geology at Kent State University. And I'll let you take it from there.
Thank you very much, Savannah. So I'm just going to start up my screen. And can everyone see the presentation at this point? So it's a pleasure to be here to make this presentation for this group. So I've been working on Lake Erie for quite a number of years now. And this is in collaboration with NASA Glenn and a number of other researchers in Ohio, Michigan, and other areas of the United States. This work is funded by the NASA Foundation, but I'm also funded by projects in Florida by the Hoover Foundation. And I want to thank the Cleveland Water Alliance for giving me the opportunity to provide this talk and look forward to the questions that you may have about it. And of course, special thanks to my postdoc, Dulcia Voris, and the students working in my lab who make all of this possible, whether they're out in the field with me collecting water samples or working in the remote sensing processing back in the lab. So we're really interested in trying to monitor remote sensing, and the difficulty with doing this, monitor the lake with remote sensing, and the difficulty with doing this, of course, is that all natural samples are mixtures. And in a lake environment, it's particularly complicated because the mixtures occur at the microscopic level because of the various types of phytoplankton that are present, color dissolved organic matter or the degradation products of chlorophyll and other pigments and other plant matter, and of course suspended sediment. And so ideally with our remote sensing approaches, we want to try and be able to separate out that information so that we can get at reliable estimates of the stuff that we really want to measure. And I started out working on these kinds of problems as a climatologist. So my background is in paleoclimate, and I've applied these same kind of methods to working at identifications of minerals in deep sea sediment cores. And it was a natural transition once I moved here to Kent State to start applying these to remote sensing problems. And so if we're going to try and identify phytoplankton from space, we're going to do this on the basis of the different types of pigments that are present. Many different types of phytoplankton and cyanobacteria have different pigments. And we'll look at a table that shows some of those different types there. And so the challenge then is to try and unmix the signatures that are coming to the satellite as part of the mixed reflectance spectra. And so if we take a look at this, much of the traditional remote sensing is dominated by estimates of chlorophyll A from space, right? But all of the major groups have chlorophyll A and carotenoids, either carotenes or xanthophylls present. And so folks have tried to make use of accessory pigments like phycocyanin, fucoxanthin, or peridinin. And usually when that's done, folks make assumptions about what's present. So for example, phycocyanin is assumed to be the dominant accessory pigment in cyanobacteria, and that there are low concentrations of red algae or cryptomonads present that might convolve or make that difficult to see. As a further sort of assumption, folks assume that phycoerythrin is present in marine cyanobacteria, but pretty much absent from freshwater cyanobacteria, but that's not always the case. Likewise, with fucoxanthin, the assumption is that fucoxanthin is found in diatoms, but as you can see from here, it's found in both the brown algae and the chrysophytes, right? So the way we're going to get around this problem in my lab is we make use of not just the bands at the red end of the spectrum where chlorophyll has a very strong peak, but all of the bands within the visible in order to do this. And so if we take a look at not some reflectance spectra, but fluorescence spectra, this is the calibration data that's available with one of the instruments that I use in my lab. This is a field instrument called a BBE fluoroprobe. And so what they've shown is typical spectra for green algae, blue-green algae or cyanobacteria, diatoms, cryptophytes, and then the degradation products of those pigments, which they refer to here as CDOM. It's also known as Gelbstoff, as one of the terms that's used for it in German, or the literal translation of it, which I love, which is yellow stuff, right? And so if we look at these spectral shapes, we can see that the blue-green algae have a spectral shape that's distinct from green algae, but the green algae, if we take a look at the green algae shape and the diatom shape, looks very similar. And in fact, if we calculate the correlation between those, you'll see that the green algae and diatom signatures are actually highly correlated, right? The other signatures that we see here are not highly correlated. And so here's that correlation space that we'll look at. And so notice that green algae and diatoms are significantly correlated here. And so when I make use of this instrument, I'm going to merge the green algae signal with the diatom signal, right? So we won't be able to differentiate between those two, but we will be able to differentiate the green algae plus diatoms from the cryptophytes and blue-green algae. Okay, so in the spectral library that I have, I also include a number of other pigments. So we include chlorophyll B, chlorophyll C. The library itself has all major pigments in it and many different sediments as well. Now, part of the reason why we use a statistical approach to unmix these signals is because all of the bands in the visible are highly correlated because of the underlying physical absorption processes that occur in the visible. And so to show that, here's the correlation of each of the bands in the visible for MODIS for one day that we happen to grab versus the reflectance spectra, a derivative spectra, the first derivative spectra, and the second derivative spectra. And the point here is, given that we have almost 25,000 measurements that are present here, all of these bands are highly correlated. And so we have to use some kind of statistical technique in order to separate out those signatures. And so the one that we use is a variation of principal component analysis that we'll look at. Another point that's important to keep in mind is if we look at the derivative spectra for different types of algae, so for example, dinoflagellates, diatoms, haptophytes, chlorophytes, cryptophytes, and cyanobacteria, you'll see that they all show a very prominent response in the red edge, right? So the height of the peak in the second derivative at the red edge is not a measure of cyanobacterial abundance or chlorophyte abundance or diatom abundance for that matter. Rather, it's a measure of the total amount of chlorophyll that's present within the system. And so from that standpoint, the red edge, which is this part of the spectrum that we're fond of using in remote sensing, gives us an indication of the bloom intensity or the size of the bloom, but it doesn't help with specificity. Okay, so what we do in our lab then is we measure water samples using visible derivative spectroscopy. We take a first derivative of those measurements. We then take that and calculate the correlation matrix of all of the bands that are present within the visible, and then decompose that correlation matrix in order to separate out all of the information that's available in the image into independent or orthogonal components. And those components then are mixtures of the constituents that we're interested in identifying. We then identify those using a stepwise multiple linear regression, right? And so if we take a look at this, here's an example of some of the ways that we can collect data. So we can collect data in the lab by filtering a sample and then measuring it with a spectrophotometer in the lab, or we can take a spectral radiometer out into the field, make measurements right on the surface with a hyperspectral sensor, which we can then compare against satellite images. And here's an example of a retrieval that we've made in the US Virgin Islands, which is one of the places that we're working with this. So if you look at our processing flow chart, this is how we make use of this. So we start with level 2 data, right? So level 2 data has been atmospherically corrected, right? So we can, one of the nice things about this approach is that the method is relatively insensitive to atmospheric errors. So we can choose different atmospheric correction routines and then pull out the same type of information from it. And I'll show you some evidence of that from some of our earlier papers. So we isolate out the water pixels from the land and cloud. So we mask out land and cloud. We then calculate the derivative of the reflectance spectra. We then decompose it using this multivariate technique that's quite well known. And that provides us with a couple of pieces of information. We get back a spectral fingerprint that we can use to identify what the material is that's present at each of the pixels. And we get a spatial map, right? And that spatial map shows us the information at each of the locations in the image. We regress the signature against that, and then we're able to transform that into a constituent map that we can use to identify the type of material that's present. And we can also extract the pixels from the image and then regress those against in situ field measurements so that we can calibrate this into known units like milligrams of chlorophyll, for example. I'm not going to show you examples of that today, but that's certainly something that we're capable of doing and that we have published papers on recently. Okay, so I mentioned that the method is relatively insensitive to atmospheric correction. And so to document that, we have a couple of slides. So this is some information that we collected with our collaborators at NASA Glenn, John Leckie, Roger Tokars, and many others. And what's shown here is our hyperspectral retrievals from Sandusky Bay and from Maumee Bay State Park. And what's clear from this is that the spectral pattern looks similar for those three different locations that are shown here. And that spectral pattern happens to correlate with one that's matches to the different types of cyanobacteria that are present within the lake. Right now, what's remarkable about that plot was that it was generated using two different atmospheric correction techniques. And you can see that we get reasonably good agreement between the two of them. So to really confirm that, though, we went and redid that experiment using both of those atmospheric correction methods at the same locations. And so that's what's shown here. So the red curves on the right are signals that were corrected using the vicarious mirror-based reflectance method that was developed here at Kent State. And the blue curves were calculated with the Michigan Tech Research Institute's vicarious blacktop-based reflectance method. And so briefly, the way the mirror-based reflectance method works is we shine the light from the sun, shines down onto a series of curved mirrors on the surface and bounces that back up to the sensor. We then use that information in order to pull out the atmosphere in conjunction with surface measurements of reflectance from the water. With the Mitri blacktop approach, they make use of an upward-looking sensor on the aircraft, a downward-looking sensor on the aircraft, and then measurements on the ground of blacktop to come up with the correction factor to pull out the atmosphere. And as you can see from those two curves, they agree very well throughout most of the visible spectrum. There's a little bit of divergence on the blue end of the spectrum, but certainly we're pulling out the same cyanobacterial signals that differ from location to location. So this was a result that we published in a NASA technical paper, and we were very excited about that because it meant that we were on the right track to an approach that was going to work in collaboration with our colleagues. So the follow-up paper was published in the Journal of Great Lakes Research in 2019, and this lays out the details of the statistical method in all kinds of gory detail if you're interested in it. If you have questions about that, I'd be more than happy to follow up with people afterwards. But what was interesting about this data set was that we collected not one, but 4 swaths within 30 minutes. And so that gave us an exceptional opportunity to measure the reproducibility of this approach and to see how it allowed us to improve the signal that we can pull out. So on the left-hand slide that we see here, this is an RGB image across the Maumee Plume, right? And the coastal waters here are rich in goethite and hematite. As we move farther offshore, we pick up some illite sediment. And of course, there are algae that are present in all of these in cyanobacteria. That lets us separate out the signal into 5 or 6 constituents that we can map to environmental variables. And it also allows us to isolate the atmospheric noise that was residual to this after the atmospheric correction, right? So with this statistical approach, we get back much greater specificity. We separate out residual atmospheric noise, and we have a high reproducibility. And so this shows the features that we pulled out from those 4 swaths that were collected within 20 minutes of each other. And so, or 30 minutes of each other, excuse me. So the shift that we're seeing here is the variability that's occurring because of the flow of the water between the times when the aircraft was able to fly back over again. Notice that in all cases, we're able to pull out that signature of the atmospheric noise, which would otherwise provide speckling into our response. And so that's that white noise response. Now, in addition to these spatial maps, one of the things we're able to show is by separating out the signal, we can boost the signal to noise ratio here, right? And so notice that the smallest signals actually get the largest boost in signal to noise ratio because we're taking a small part of the signal and isolating it from the larger part of the signal that would otherwise swamp it out. And so in that way, we're able to boost the signal to noise ratio by almost a factor of 20, right? Now this is a software-based boost, so we don't have to do anything different in the hardware in order to get this benefit, which is a very desirable outcome from this, because it allows us then to use this with sensors that otherwise have a low signal to noise ratio that wouldn't make them suitable for doing the kinds of quantitative work that we're studying. And the outcome from this, when we look at this, is a series of spectral shapes. Those spectral shapes here are shown as the colored curves in orange, tan, and blue, for example. And then the black curve represents the average to that, and our gray, thick gray curve is our best fit to that based on the spectral library that we use for identification. So the correlation coefficients then show the magnitude of the fit that we're able to make to each one of those constituents that we pull out, and the panel down here shows the uncertainty. So our reproducibility of this is plus or minus 3%, and we're able to identify the types of materials that are present within each of these. All right, so that provides some information about the basis of the method. One of the advantages of this approach actually is we can take each one of these coefficients that we have here, and if we square them and sum them, it tells us how much of the information in each one of the bands in this hyperspectral sensor is related to each one of these signatures that we're pulling out. And so that's what we're showing in this next plot here. And so when we look at this, what we see is the dark gray over here represents the largest part of that atmospheric residual, which is aerosol scattering that we're getting from. So that could be aerosol scattering from lake aerosols. It could be from terrestrial aerosols or smog that's in the system, for example, right? The blue, which represents the largest fraction of variance, in this case, mapped to a mixture of sediment and accessory pigments. The orange mapped to diatoms, sediment, and accessory pigments. The green was the signature of goethite, and the light green and the yellow-orange here represent cyanobacteria and a separate constituent of hematite and cyanobacteria. And then at the top, the light gray represents the noise in each one of the spectral bands, which we're able to isolate from the signatures of interest. Okay, so one important feature to point out about this is if you look at the bands between 670 and 700 nanometers, this is towards that red edge. And notice that all of these bands are composed of signal from more than one of the constituents that are present. Now, remember, with the approach that we're using here, we separate out the information in terms of orthogonal or independent components. So if you hadn't done this, that information would be contaminating the signal that you're interested in, right? And so this is one of the advantages that we get from this approach. Okay, so that brings us to the variability part of the signal, and we'll look at how the method compares with the operational approach that's being used right now. So the first image that we're going to look at, we have some field data go along with that, and so this was August 2nd of 2018. This is an image from MODIS Terra. We're using MODIS Terra not because it's our favorite sensor, but because it was the sensor that gave cloud-free conditions on this particularly cloudy day. Given our alternative, we would much rather work with Sentinel-3A and B, which provide 300-meter resolution and more bands in the visible than MODIS Aqua or MODIS Terra. So on this day, I was out with some assistants, and we sampled at each one of these locations across Lake Erie. So to orient you, here's the Maumee River, this is Michigan, this is the Huron River in Michigan, and then the Detroit River. The white area is cloud or land, right? Notice that there is one point in the Maumee plume with this series of data, that's the WLE02 point. WLE4 is out towards the center of the Western Basin, and then these 3 points, which I called the Detroit plume transect points, monitor into the Detroit plume and along the Michigan rivers. So the operational product from this day looks like this. And so signal that's below detection is shown here as black, gray is cloud, and the tan represents land. You can see the location of prominent features there. And the detection limit with the operational NOAA approach is 20,000 cells per milliliter, right? If we look at the application of our KSU method to this, this is what we get for the cyanobacterial signal, which is identified as correlating with the phycocyanin signal. So notice that we pull out coherent signal in the Maumee plume. we pick up a secondary cyanobacterial bloom, a small one in the north, which is below the detection limit of the operational signal. Okay, now in addition to that, that one field, we also pull out additional fields which we can identify in comparison with that spectral library. So on this case, the leading component was correlated with hematite and chlorophyllite A, one of the degradation products of chlorophyll, and notice that it's reaching its maximum values along the coast in shallow water or close to the mouths of rivers where you would expect to see sediment and decaying organic matter carried into the river, into the lake. The second component is that cyanobacterial component that we mentioned that has that dual nature with the larger bloom in the south and a smaller bloom in the north associated with either the Huron River or the Detroit. The third component correlates with hematite and chlorophyll C, and that's found in coastal waters near river mouths. And finally, that fourth component, now when we look at that, we see that correlates with kaolinite, which is a sediment, and that sediment signature is strongest associated with the Huron plume. We can see that the values don't extend up into the mouth of the Detroit River, so this is either a pulse that was flushed out of the Detroit, or it's the signature coming from the Huron proper. Now notice that the sediment is higher in the northern part of the basin than in the southern part of the basin, and we'll see that signature when we look at our validation data. Okay, so the validation data that we collected was at these 1, 2, 3, 4, 5 points, right? So we have the 3 points in the Detroit plume, the WLE4 point, and the WLE2 station, which is the one station that was in Maumee Bay. We did profiles with the fluoroprobe, and when we do that, what you see is there's signature of biogenic particles that are dominating in the south. If we look at the total chlorophyll concentration from the signature and compare that with the yellow stuff or a Gelbstoff signature or a CDOM, we see that it's highly correlated with the biogenic particles, which makes sense because that's the source of the CDOM. The signature that's also shown here is the suspended sediment estimated from the fluoroprobe. This is presented here as beam attenuation coefficient, which is driven by absorption and backscatter in this case. And it's highest in the north and decreases to the south. If we go up to the top panel again, you can see the Secchi measurements that are made here. And so the Secchi in the southern part of the transect is dominated by biogenic particles. In the northern part of the transect, it's dominated by suspended sediment. So all of those observations agree nicely with the interpretations that we get from the KSU method applied to that Modus Terra image. But we can also compare this on a sample by sample basis. And so one of the things that's interesting about the fluoroprobe is that you can present the results either as cells per milliliter or as fractions of the total chlorophyll. And so in this way, when we look at this, we can see that green algae and diatoms were present throughout the transect. The cryptophytes and the blue-green algae generally dominated in the southern part of the transect and decreased. Now, it's worth noting that if we look at the average chlorophyll abundance in these transects on this day, what we see is 27% of the chlorophyll was from cyanobacteria. When we look at the variance explained by what's extracted from the Modus image using the Kent State approach, we get 25%, which agrees quite nicely. We also made laboratory measurements. So we collected water samples and sent them off to an independent lab for analysis. And so that lab measured extracted phycocyanin. They also measured cell counts for us. And all three of those methods, so laboratory-based phycocyanin measurements or laboratory-based independent cyanobacterial cell count densities, agree with the fluoroprobe estimates of chlorophyll A and account for 82 to 84% of the variance within the data set. Recall that this one point, this is the point from Maumee Bay, which is quite distinct from the other points across the transect. Now, in addition to the identification of the cyanobacteria that are present, we can also show that we had laboratory extracted measurements of chlorophyll C. Those agree with the chlorophyll A estimates from the Flora probe, and chlorophyll C is known to be a constituent or an accessory pigment that's present in cryptophytes, which agrees with the identification that we made from the Flora probe measurements. And finally, we can look at the green algae and diatom and see that they're inversely correlated with the suspended sediment signature that we pulled from the satellite, which makes sense because when there's less suspended sediment, we would have better light conditions and thus higher abundances of algae and vice versa. All right, so if we go and look at the detection limit for this, we come up with a detection limit of 1,000 cells per milliliter at the intercept for these measurements for comparison with the 20,000 cells per milliliter for the NOAA-CI method. And this accounts for almost 90% of the variance within the data set. Okay, so we can continue using this method through the season, which we did. So here's the signature from August 13th of 2018. This is the NOAA product. This is close to or at the maximum extent of the bloom at this time per year. Notice that there's no bloom detected within the Detroit plume, the northern part of the Western Basin. There's no signal detected in the Central Basin. When we apply our method to this, we're able to pull out signature from all of those parts of the basin, which is consistent with the point that I made about our ability to measure well below the detection limit of the operational signal. If we look at the spectral shapes that we can pull out from Modus aqua in this case, notice that there's a strong red edge response in all four of the signatures that we're able to pull out from this. And so if you were using a method that didn't allow you to separate out the signature into independent components, you're going to convolve information from one type of material to another in the signals that you're able to pull out from this. So in this case, the leading signature correlated with phycoerythrin and some suspended sediment. The second signature was a mixture of chlorophyll A and suspended sediment. The third was hematite, which is an iron oxide. And the final constituent was chlorophyllite A and chlorophyllite B, degradation products of chlorophyll A and chlorophyll B, respectively. So at this point, we were excited with the results that we were getting from the Flora probe, and so we decided that we wanted to increase the amount of data that we're able to collect on each of our profiles. And so I developed a technique to tow the Flora probe behind our instruments, behind our boat, excuse me, to increase the sample resolution. So we're able to go from collecting 5 or 6 stations per cruise, as shown with the profiles here, to having over 5,000 or almost 6,000 data points across the transect. And what's shown here is the total cell counts for the measurement across this plume. So this is now the maximum of cell counts that we're able to obtain from the Maumee plume, and then decreasing as we go to the north into the Detroit plume. One of the things that's nice about the Flora probe is that it also gives you information about the surface temperatures, and so we can map out the distribution of the surface temperatures from the Maumee plume, compare that with the Secchi depth, and show that the signals that we get from the towed measurements are consistent with the signatures that we get from the vertical profiles, which we do on the return trip. So we tow from south to north or from north to south, and then on our return trip, we collect vertical profiles and water samples for validation of the towed active Flora probe instrument. And so this shows some of that calibration. So here's the tow data in conjunction with our profile measurements, and the green are laboratory measured chlorophyll. For comparison, these have been corrected for degradation products of chlorophyll, so that we're looking at a clean chlorophyll signal, and you can see that these agree quite nicely with the measurements that we made from the towed system. On the right, we have the yellow stuff measured by the Flora probe across the transect, and we can superimpose on that the signature that we pulled out from the satellite that relates to the yellow stuff that's present. Now, at this point, we haven't corrected for the difference in pixel size. So the pixel sizes on MODIS are at 1 kilometer resolution. The data that you're seeing from the fluoroprobe is at 8 meter resolution, which is why it looks like a fuzzy caterpillar, why there's so much more variability in the measurements that we made from the toe. But we'll correct for that as we move along and show you the results we get from that. Okay, so one of the things to note on this is that the maximum cell count here was less than 8,000 cells. So when we compare that with the signature from the detection limit for the operational method, what you'll see is that all of this signature across the basin is below the detection limit. And sure enough, when we look at the signature from Modus Aqua for that day, we see exactly that case. So all of the signature here is below 20,000 cells per milliliter. In fact, we've demonstrated by towing the fluoroprobe across this that it's down around 1,000 to 8,000 cells per milliliter. So when we apply the Kent State method to this again, we don't reach that detection limit. We're still able to pull a signal out of this despite the fact that the signature is much lower. In this case, the signature is dominated by suspended sediment and degradation of products of chlorophyll, although we know there's cell counts that were present based on the fluoroprobe data. And notice that we do get a strong red edge response in more than one of the constituents that are present. So what we can do is we can take the fluoroprobe data and use the fluoroprobe data to regress this against the satellite data to see what the detection limit is for this. And before we do that, we're going to take the data along the toe. We're going to resample it to the same resolution, that 1 kilometer resolution for the satellite, so that we can compare apples to apples. And when we do that, this is the result that we get. And so this is an exciting result because it demonstrates that even when we have 29 data points for comparison, we still get linear relationships that are statistically significant and explain 70 to 80% of the variability within the data set. So in this case, we're showing the relationship between the green algae and diatom signal that's extracted from the fluoroprobe versus the degradation products and sediment that are seen within the satellite. Or looking at another one of the constituents, we can compare the chlorophyllide concentration with the yellow stuff measured by the towed fluoroprobe. If we take the total cell count information from the towed fluoroprobe, we can regress that against all of the signatures that we extract from the satellite and come up with a statistically significant regression that explains 87% of the variability in this and shows again that our detection limit with these 29 data points is down around 1,000 cells per milliliter, which is considerably lower than the operational limit that was shown by the method that's currently being used in Lake Erie. Okay, so we have multiple measurements from multiple days that are consistent in terms of their detection limit. And so one of the questions that then arose after I started showing or sharing this information with others was, well, that's all very interesting that you can do this for a couple of days in 2018, Dr. Ortiz or Joe, but can you do this back through time? And so we went back to the lab and analyzed data from the Modus Aqua and Terra signatures going back to 2012, and this is what we were able to pull out. So we pull out 5 different patterns that are present within those 7 years of data. We show that they're highly reproducible, and this is notable because Modus Aqua and Terra come over at different times of the day. One comes over in the morning, one comes over in the afternoon. The signature of these satellites or their measurement capabilities has also been decreasing with time because they're now on the order of 15 years old. And so even though the signatures of the satellites are degrading with time, we're still able to pull significant signal out of this that we can then compare against known constituents and use to interpret what's happening within the lake. Okay, and just as we did for the hyperspectral sensor from NASA Glenn, we can show what fraction of the signature is associated with each one of the bands. And we see that here again, the bands that are close to the red edge include signature from more than one constituent that's present. And so if your approach to monitoring chlorophyll is based on the red edge only, there are going to be some times when you make measurements that are not going to be based on just chlorophyll that's present in the water, but rather a mixture of chlorophyll and other materials that's present. Okay, so that brings us to 2019, right? If we look at the 2019 data, this is data from the HAB-GRAB 2019. So there were 11 vessels that were out on Lake Erie on that day. We were out on one of these. We towed the fluoroprobe again from south to north. These are the 4 signatures that we're able to pull out. So we pull out a green algae or non-HAB related algae signal as one constituent. We pull out the HAB-related cyanobacterial constituent as a second. There's a suspended sediment signal, and then a cryptophyte signal as the fourth. Notice that the HAB signature and the cryptophyte signature have very similar spatial patterns, but their spectral signatures look different, right? And so we're able to separate them on the basis of their spectral signatures, despite the fact that they look quite similar in terms of their spatial pattern. Well, one of the reasons why their spatial pattern might be similar is because both of these groups contain phycocyanin or phycoerythrin, right? Both cyanobacteria and cryptophytes. But they have different pigments that are also present, and they're presumably present in different abundances or relative abundances, which is why we're able to separate out these signatures using this method. And to validate this data, here's the signature that we get from the fluoroprobe on this day. So I'm showing it now instead of as cells per milliliter, as micrograms per liter of chlorophyll A. And so the blue signature is the cyanobacterial signal, and we see that that dominates in Maumee Bay. The green signature is the signature from the green algae, and we see that that is absent from Maumee Bay and has the same spatial characteristics across this as we saw with our tow. And finally, the cryptophyte signal is correlated with the signature from the cyanobacteria, but found in much lower relative abundance, right? So there was a question about the numbers on the axes here. These are standardized units. So the way this is calculated, we subtract the mean and divide by the standard deviation, and then we separate that out. So these are partial standardized scores. If we wanted to convert these to geophysical units like micrograms per liter, all we have to do is regress the data that we have for the calibration against those values that we see here. All right, so if we compare this with the operational product, what we see is the operational product identifies the entire bloom as cyanobacteria and is unable to separate out the signature from Maumee Bay with the rest of the signals that are present within the Western Basin. And so it's clear that if we look at this, we can see that the offshore portions of the bloom are associated with the first component we extract, and the onshore portions of the bloom are associated with the second component we extract. The reason why the signature is not separated in the operational product is because both of them have a very strong response in the red edge, which are the only bands that are used in the operational product. So in order to differentiate between these two populations, we have to make use of information from other parts of the visible, which is what we've done with this approach, and what allows us to separate out the signature of the cyanobacteria from the non-HAB related algae. And of course, this allows us then to look at the signature in detail. So here's those two constituents shown for the beginning of the bloom. So we processed our first image this year on 6/28/19, and you can see how the signature of these two different parts of the community structure varied through time, right? So notice that the green algae are spread more throughout the basin. There's clear evidence of mesoscale features that are showing up here that are driven by local changes in the lake currents or upwelling or downwelling or wind-driven currents. The same is true about the HAB constituents, and you can see that those are concentrated in Sandusky Bay and Maumee Bay. And so this is the first couple of days of that, and we can extend farther into the season to see how it expands. This is close to the maximum of the extent of the cyanobacterial signal observed with our approach. For comparison, this is the first day that the signature jumps up above about 20,000 cells per milliliter at the beginning of the cruise, or beginning of the season, excuse me. And this was something that we predicted we would be able to do on the basis of the results that we generated in 2018. And our results this year have borne that capability out. All right, so so that's been a description of the rationale behind the method that we make use of in Lake Erie. We've used this in a number of different environments, small lakes in Ohio, in San Francisco Bay, and in systems in Florida and the US Virgin Islands. This tracks the contribution of different types of phytoplankton, right? So we can't identify individual species of phytoplankton, but we can certainly separate out the dominant groups that are present within a given basin, which is a big advantage over many other approaches that are being used for remote sensing as well. And the strength of this method is that we make use of all of the bands that are present within the visible, whether it be multispectral or hyperspectral signatures, and we've applied the method to a number of different satellite sensors with different spatial resolution and different repeat times. What's nice about this is we're now at the point where we can generate daily measurements with this using the Sentinel-3A/B. We're also planning to migrate over to the VIIRS sensors as well to fill in gaps in time and so on. So I hope you've enjoyed the presentation that I made today and learned some interesting things that might be of use to in your applications. We've published a number of papers that are related to these methodologies and to the work that we're doing here in Lake Erie. So this is a description of them. If you'd like to see my full CV or all of the information, you can find that on my webpage, my homepage, or in my Google Scholar or ResearchGate entries. And with that, I will take questions. Thank you very much.
Thanks, Joe, for that great presentation. I'm just going to read out some of the questions that we've got here. And again, if anyone wants to submit a question, please go ahead and do so. So one of the questions is, can you make measurements or models at depth? For example, a sinking dead bloom.
So the question was, can we make measurements at depth? So the signals that we're measuring are integrated over the first optical depth. So we're seeing signatures that are related to the information from about the surface down to where you stop being able to see a Secchi measurement with the Secchi depth. Now, with that being said, in many cases in relatively shallow bodies of water, what you'll find is that the surface signature is highly correlated with the subsurface signatures that are made throughout the water column. And in fact, with the fluoroprobe data that we're collecting, we're towing that behind the boat, so it's mixing signatures over about the upper 2 meters or so of the signal that we're trying to get from. So thank you, that's a good question. And as you saw from the results, we can see the degradation products of blooms and differentiate them from chlorophyll.
Great, thank you. Another question was, is atmospheric noise from smog or haze also screened out as interference?
Yeah, so if the signatures are not correlated with the signature from the constituents in the water, then yes, it would be separated out as a separate constituent. So in this case, the smog is going to be removed. Most of that's removed by the primary atmospheric correction, and then the secondary signature that you see is that scattering component that we're able to separate out from.
Great. Okay, and then there was another question. How different would the methodology be applied in salty or highly saline waters?
Oh, that's a great question, right? So, so we have used this approach in the waters around the U.S. Virgin Islands. So it does work in saline environments. One of the things that that we'll need to do to really bring this up to complete utility in those kind of environments is to upgrade the library that we have, right? So our library right now is tuned for freshwater environment. But as I pointed out in the talk, we can identify the constituents using the derivative reflectance spectra obtained from a number of different sources. We can also calibrate against in-water measurements that are made. So that adds to the versatility of the approach.
Perfect. Thanks, Joe. And then another question from Patrick. What is your conservative estimate of sensitivity compared to existing products?
So the sensitivity compared to existing products, well, we demonstrated that our detection limit is 20,000, is about 1,000 cells per milliliter. The current product that we compared against is the operational one, which has a detection limit of about 20,000 cells per milliliter. So it's about a factor of 20 improvement over existing methodology.
Great. And then Ed asks, has anyone ever correlated CL sediment with phosphorus loads in the sediment?
Yeah, that's a good question. We're in the process of working our way back through the library of or the archive of remote sensing images, and that's one of the topics that we're very interested in, is looking at the difference in sediment loading and the responses that we get from time to time.
Great. And then Ed also asks, does your data analysis to date indicate Lake Erie HABs are better or worse compared to 2018?
So we haven't analyzed the full time series yet. 2018 was expected to be a large bloom. It turned out this year that it was not quite as bad as it could have been, because this was quite a wet year. Some of the reports that I've heard through posts on social media suggested that part of that might have been because of decreases in phosphorus loading due to changes in land use planning. But I think we'll have to wait to see what the data bears out on that.
Great. Okay. And I just want to remind everyone that you can keep submitting your questions. We've got another one here from Michael. How does the time of day the satellite flies over affect detection of cyanobacteria? Does the cyanos daily migration up and down in the water column affect detection in any meaningful way?
Yeah, that's a good question. So cyanobacteria do migrate, and that's going to be an issue with any type of remote sensing method that that's employed. One of the advantages of this approach is that we have a lower detection limit. So we should be able to see smaller signals when there's less cyanobacteria up near the surface. We've also have indications that there is a correlation between the signature at the surface and what's occurring subsurface. So one of the measurements that I've made as part of the towing operations that we've done is to go in and we start out taking a profile, then we tow, we go all the way to the end of our tow, come back, and then take profiles back, ending with a profile at the same location. And when we do that, what I found on the days that we compared that is if you integrate the total signature from the bottom of the lake to the top of the lake over that time period, you'll get a ratio that's close to 1 for those, suggesting that while there is some redistribution over that 7-hour time period, the samples are not, they're still well correlated because it's a relatively slow-moving process. So some to be concerned about, but certainly an issue for all remote sensing approaches.
Great. Okay. And then how do you determine which VPCA component correlates to which pigment?
So the correlation to each pigment is done using forward stepwise principal regression. In this case, that's a regression of the independent components against the spectral library constituents. In addition to that, we use a statistic called the variance inflation factor, or VIF, in order to ensure that we don't overfit the model. And so with unmixed data used with stepwise regression, the variance inflation factor is usually allowed to go up to about 4 or 5 and considered acceptable. In our case, since we're using unmixed data, we actually see much lower variance inflation factors, and we rarely go up above 1 or 2. In fact, we don't allow the signal to go up above 2 in terms of the variance inflation factor.
Great. And Ed also asks, with the lower detection limit, can you measure/monitor CB activity during the winter season and then compare this from winter to winter for predicting summer blooms?
In principle, we should be able to do that, yes. One of the points that I made in earlier statements was that we can use this approach earlier than the traditional approach and later than the traditional approach, because of the fact that we can separate out the signal. So early in the season, there's lots of suspended sediment, and if you try to apply traditional remote sensing approaches with all of that suspended sediment in there, what's going to happen is the brightness from that sediment is going to cause problems. It's going to add bias to the chlorophyll estimates. With this